Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The pursuit of scientific truth often navigates a delicate course between the ethereal realm of mathematical abstraction and the concrete domain of empirical verification. Few moments in the history of physics illustrate this synthesis more powerfully than the series of experiments conducted by Heinrich Hertz in Karlsruhe during the late 1880s. His 1887 paper on electromagnetic waves in air and their reflection stands as a monumental landmark, a work that furnished the incontrovertible physical evidence for what had hitherto been one of the 19th century's most profound and challenging theoretical constructs. It was in the confines of his laboratory, with apparatus of remarkable simplicity, that Hertz gave tangible form to James Clerk Maxwell's equations, transforming them from a set of elegant but unproven mathematical expressions into a description of a physical reality that would fundamentally reshape the modern world. This essay will explore the genesis, execution, and enduring legacy of this seminal paper, arguing that its true significance lies in its definitive unification of light, electricity, and magnetism into a single, cohesive framework, thereby providing the empirical capstone to classical electromagnetism and unwittingly laying the groundwork for the technological age. The intellectual landscape upon which Hertz embarked his investigation was dominated by the theoretical edifice constructed by James Clerk Maxwell 2 decades prior. In his 1865 treatise, A Dynamical Theory of the Electromagnetic Field, Maxwell had achieved a grand synthesis of the then-known laws of electricity and magnetism. His four famous equations described a universe wherein electric and magnetic fields were inextricably linked, a dynamic interplay where a changing magnetic field induced an electric field, and, most revolutionary of all, a changing electric field induced a magnetic field. This last component, the displacement current, was a purely theoretical invention, a mathematical necessity for the consistency of the equations. Its inclusion led to a startling prediction: the existence of self-propagating transverse waves of oscillating electric and magnetic fields. The equations further predicted the speed of these waves, a value derived from two fundamental constants of the laboratory: the permeability and permittivity of free space. The calculated velocity, 1 over the square root of the product of mu0 and epsilon naught, yielded a figure astonishingly close to the measured speed of light. This numerical coincidence was too profound to be accidental. Maxwell proposed that light itself was an electromagnetic wave. For over 20 years, this breathtaking idea remained an article of faith for a select few, a theoretical masterpiece awaiting its experimental apostle. The direct impetus for Hertz's work came from his mentor, Hermann von Helmholtz. In 1879, the Berlin Academy of Sciences, at Helmholtz's suggestion, offered a prize for the experimental demonstration of a deconsequence of Maxwell's theory, specifically proving that a changing electric polarization in an insulator produces the same magnetic effects as a conduction current. As a young student under Helmholtz, Hertz had considered the problem but deemed the experimental challenge too formidable. Yet the question lingered. Years later, having secured a professorship at the Technical High School in Karlsruhe, he stumbled upon a pair of induction coils while organizing his laboratory. A behavior reminded him of the old prize problem. This time, armed with greater experience and resources, he embraced the challenge. The intellectual stage was set for a direct confrontation with Maxwell's theory. While theorists like George Fitzgerald in Ireland had speculated on the means to generate such waves, the world of physics awaited a definitive, unambiguous demonstration that these ethereal disturbances could be created, propagated through space, and detected. The genius of Hertz's 1887 paper resides in the elegance and lucidity of its experimental design. His apparatus, a far cry from the colossal instruments of modern physics, consisted of two primary components. The transmitter, now known as a Hertzian dipole, was essentially a high-voltage induction coil connected to two polished brass knobs separated by a small air gap. Attached to these knobs were larger conductors, often brass plates or rods, that acted as a capacitor and antenna. When the induction coil generated a sufficiently high voltage, a powerful spark would leap across the gap. This spark was a violent, oscillating discharge of electricity, a rapid sloshing of charge back and forth across the dipole at a very high frequency, on the order of many millions of cycles per second. According to Maxwell's theory, this accelerating charge should radiate energy away in the form of electromagnetic wave. The detector was even simpler, a testament to Hertz's ingenuity. It was a simple loop of copper wire, incomplete save for a minuscule, adjustable gap between its two ends. This loop was designed to have a natural resonant frequency. When the loop was brought into the vicinity of the transmitter and oriented correctly, The oscillating magnetic field of the passing electromagnetic wave would induce an oscillating current within the wire. If the wave's frequency matched the loop's resonant frequency, this induced current would become strong enough to create a voltage across the gap sufficient to produce a tiny, faint spark. This minuscule spark, often observable only in a completely darkened room, was the signal. It was the whisper of a distant electrical disturbance made visible. The ability to generate a spark in one circuit by the action of another across open space with no connecting wires was itself a remarkable feat. It was Hertz's subsequent experiment, detailed in the 1887 paper, that elevated the work to the highest echelon of scientific discourse. The paper's title, On Electromagnetic Waves in Air and Their Reflection, points directly to its central triumph. Having established his ability to transmit and receive these invisible emanations, Hertz set out to prove they behaved like waves. He performed the classic experiment for demonstrating wave-like character inducing interference. He placed a large, flat sheet of zinc, a good electrical conductor, at the far end of his laboratory, creating a reflective wall. His transmitter was positioned several meters away. Aimed directly at this metallic surface, the outgoing waves from his spark gap travelled towards the zinc sheet, reflected off it, and travelled back towards the source. The critical step was what he did next. He systematically moved his detector loop along the line between the transmitter and the reflecting wall. The results were unequivocal. He discovered the distinct pattern of nodes and antinodes. At certain specific locations, the detector loop would produce a strong, bright spark, indicating a maximum of electromagnetic energy. These were the antinodes. At other specific locations, precisely halfway between the antinodes, the detector loop would show absolutely no spark, regardless of its orientation. These were the nodes, points of complete destructive interference. This pattern is the definitive signature of a standing wave, formed by the superposition of the incident wave and its reflection. The outgoing and returning waves were interfering, cancelling each other out at the nodes and reinforcing each other at the antinodes. This observation alone was a powerful confirmation of the wave-like nature of the phenomenon. The experiment, however, yielded a quantitative result of even greater importance. By carefully measuring the distance between two consecutive nodes, Hertz could determine the value of half a wavelength for radiation. He found the wavelength to be several meters long, vastly longer than the waves of visible light but unmistakably a wave measurement. The final, crucial piece of the puzzle involved calculating the wave's velocity. Hertz could estimate the frequency of the oscillations in his transmitter circuit from its electrical properties, its inductance and capacitance. Applying the fundamental wave equation, velocity equals frequency multiplied by wavelength, he calculated the speed of his invisible waves. The value he obtained was approximately 3 times 10 to the 8 meters per second. It was the speed of light. The circle was complete. The waves generated by an electrical spark in his laboratory, propagated through the air, and reflected from a metal sheet, travelled at the same speed as light from the sun. Maxwell was right. The immediate impact of Hertz's paper was profound and transformative. It settled, with one decisive stroke, the long-standing debate between Maxwell's field theory and the older, competing action at a distance theories of electromagnetism. The ability to generate, control, and measure these waves in a laboratory setting provided incontrovertible proof that electromagnetic effects propagate at a finite speed. The work was hailed across Europe as a triumph of experimental physics, a perfect symbiosis of theoretical prediction and empirical confirmation. Lord Kelvin, a towering figure in British science who had long held reservations about Maxwell's more abstract concepts, was famously won over by the clarity and force of Hertz's demonstrations. The discovery solidified the unification of optics with electricity and magnetism, revealing that visible light was merely a small sliver of a vast, unseen electromagnetic spectrum. Physics at a new playground it had provided. The seeds planted on Hertz's laboratory bench grew with astonishing speed, though their eventual applications far exceeded anything he himself envisioned. Scientists like Oliver Lodge in Britain and Augusto Ricci in Italy immediately began replicating and extending his experiments. Lodge, for instance, developed a more sensitive detector known as the coherer, which became a critical component in early wireless systems. The most famous inheritor of Hertz's legacy was Guglielmo Marconi, whereas Hertz, the pure scientist, famously remarked on the uselessness of his discovery, stating it was merely an experiment that proved Maestro Maxwell was right. Marconi, the inventor and entrepreneur, saw its immense practical potential. He systematically adapted and scaled up Hertz's apparatus, increasing the power of the transmitter and the sensitivity of the receiver, with the explicit goal of long-distance communication. The direct lineage from Hertz's oscillating dipole and resonant loop to Marconi's first transatlantic wireless transmission, and subsequently to the entire global infrastructure of radio, television, mobile telephony, and Wi-Fi, is unbroken. Every modern antenna is a conceptual descendant of the simple device, Hertz first sparked into life in Karlsruhe. Hertz's work, for all its brilliance, was a product of its time and contained elements that would only be understood by later generations. He was puzzled by a slight discrepancy in his measurements, which suggested the waves travelled slightly slower along conducting wires than in free air. This anomaly was later explained by Arnold Sommerfeld's more sophisticated analysis of wave propagation along a finite conductor, a waveguide effect beyond the scope of Hertz's initial understanding. More poignantly, in the course of his experiments, Hertz stumbled upon another great secret of nature, a phenomenon that would become a cornerstone of the next physical revolution. He observed that the spark in his detector's gap jumped more readily when it was illuminated by ultraviolet light. This photoelectric effect, as it came to be known, was a hint that the interaction of light and matter was more complex than classical wave theory could accommodate. Hertz, with his focus squarely on confirming Maxwell's theory, dutifully recorded the observation as a curious side effect and moved on. It was a serendipitous discovery he treated as a minor distraction from the main prize. Nearly 2 decades later, a young patent clerk named Albert Einstein would provide the correct explanation for this effect, proposing that light energy is quantized into packets, or photons. This explanation, which relied on the very effect Hertz had cast aside, would help launch quantum mechanics and earn Einstein his own Nobel. In conclusion, Heinrich Hertz, his 1887 paper on electromagnetic waves in air and their reflection, represents an apotheosis of 19th century physics. It stands as a paragon of experimental investigation, where conceptual clarity and meticulous execution combined to answer one of the most profound scientific questions of the era. By generating electromagnetic waves and demonstrating that they reflect, interfere, and travel at the speed of light, Hertz provided the final, irrefutable proof of Maxwell's grand theoretical synthesis. He rendered the invisible visible, the abstract tangible, and the theoretical real. The work closed the book on classical electrodynamics, unifying 3 seemingly disparate forces of nature into a single, elegant whole. At the same time, it unknowingly opened the first chapter of the electronic age, creating the physical basis for a communications revolution that would shrink the globe. And in a final, beautiful irony of scientific history, his experiments contained a ghost in the machine, a subtle anomaly in the behavior of a spark that hinted at the quantum world to come. The legacy of this single paper is therefore twofold. It is both the capstone of a completed intellectual edifice and the foundational stone for another, one whose construction continues to this day.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.